Throw a ball straight up and catch it at the same height. Ignoring air, it lands in your hand with exactly the kinetic energy it left with. Not roughly, exactly. Last time we defined a conservative force, one whose work between 2 points is the same along every path. Today we prove what that definition guarantees: zero net work around any closed loop, and we discover where the energy goes when the guarantee breaks. Here is the setup. Picture a conservative force field filling the plane. Arrows at every point showing the force an object would feel there. Mark point A at coordinates 1, 0, and point B at coordinates 0, 1. Path 1, the upper curve, carries an object from A to B. Path 2, the lower curve, returns it from B back to A. Together, the two curves form a closed loop that starts and ends at A. The claim: the total work the conservative force does around this loop, out along path 1, home along path 2, is exactly 0. Work adds leg by leg. Along path 1, the work W1 is the integral from A to B of f sub c dot dr taken along the upper curve. Along path 2, the work W2 is the integral from B to A of f sub c dot dr taken along the lower curve. The total work around the closed loop is simply their sum. W equals W1 plus W2, one integral out, one integral home. Look at what we have. The two integrals run between opposite limits, along different curves, through different parts of the field. Written this way, nothing about them looks equal and nothing looks ready to cancel. The entire proof is one piece of bookkeeping on the second integral. Here is the bookkeeping. Reversing the limits of an integral flips its sign. Running path 2 from A to B instead of from B to A reverses every displacement element dr, so W2 equals minus the integral from A to B of f sub c dot dr along path 2. Substitute that into the sum. The loop work W becomes the integral from A to B along path 1 minus the integral from A to B along path 2. Now both integrals share the same endpoints and the path independence strikes. The force is conservative, so the trip from A to B does identical work along path 1 and along path 2. Equal integrals, opposite signs, they cancel and W is 0. Nothing depended on our particular loop, so the result is general. The closed loop integral of f sub c dot dr vanishes. The work done by a conservative force around any closed path is 0. Now the physics. Take an object near the Earth's surface and choose the object alone as the system. Throw it straight up. Once it leaves the hand, gravity acts as an external force on the system, and on the way up, it does negative work. The object's kinetic energy drains away until, at the highest point, the kinetic energy is 0. Then everything reverses. On the way down, gravity does positive work, feeding kinetic energy back in, and when the object returns to its starting height, ignoring air resistance, it arrives moving downward with exactly the kinetic energy it began with. The flight is a closed path, and every bit of kinetic energy gravity removed, gravity returned. The energy was borrowed, not lost. Now redraw the boundary. Let the system be the object and the Earth together, with no other external forces acting. The same gravitational pull is now an internal force, and as we showed last time, a conservative one. It acts on both bodies with equal and opposite pulls. As the object rises, the system's kinetic energy decreases, mostly because the object slows, but the Earth also picks up a tiny, imperceptible kinetic energy. And since the Earth now sits inside the system, we must count it. When the object returns to its original height, all of the system's kinetic energy is recovered, even though a small share was momentarily parked with the Earth. Internal and conservative still means fully recoverable. Widen the boundary once more and let the air in. Air resistance now acts as an internal force too, but a non-conservative one. Like the sliding friction from last time, it always opposes the motion, so it does negative work on the way up and negative work again on the way down. The kinetic energy it removes never comes back. It becomes thermal energy, random kinetic energy scattered among the air molecules, the molecules of the object, and, to a smaller extent, the Earth. The object lands slower than it left. No rerun of the flight can gather that energy back. It is spread over countless molecules moving in random directions, and it is not recoverable. The loop theorem tells us what each kind of force does to the energy books. When a conservative force removes kinetic energy, the loss is alone. The closed loop work is zero, so on any round trip the energy comes back in full. When a non-conservative force removes kinetic energy, the loss is permanent. The energy disperses as thermal energy and cannot be reclaimed. The recoverable share deserves its own account, and physics gives it a name. The change in the internal potential energy of the system, the measure of lost kinetic energy that can be recovered. It obeys a clean principle. In a closed system where only internal conservative forces act, the change in kinetic energy plus the change in potential energy is zero. What we still owe is a formula. How to compute that potential energy directly from the force. That is exactly where we go next. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.